All right, so we talked about means, variances in the last video. We'll now look at group data and some other character statistics that we'll be calculating from our data. So let's see. I think this one was in the previous. Let me see if I can get this minimized. So we left off. We were talking about means and variances. So we're going to talk about something very similarly related, but a little different, which is weighted means. So previously, if you want to think about it, we could have rewritten our mean. In fact, um, switch this over, kind of show you this way. So before we were calculating our mean like this. Right? Oh, okay. So we had our mean equation. We really could have rewritten this as x1 over n plus x2 over n plus x3 over n, right, etc. Another way of thinking about this is basically every single x value, we were giving the exact same weight, which is it was just one out of however many observations we had. Right? Well, what happens if the data we're looking at represents a different number of people, right? So that's when we're going to need to calculate a weighted mean, where the weights won't be the same. So, maybe I'm wanting to look at fast food sales and I can see the data by company. Well, if I want to find the average, hamburger sales of fast food places or restaurants, I know that the McDonald's number, that's the average across, I don't even know how many, probably maybe millions of stores, I don't know, across the world. Whereas like Jim's Burger Shack, right, some local burger place, is only represents one firm. So should I really be giving them the same weight by simply treating them both as one observation? The answer is no, right? So a lot of the times we might not have the original data, and all we can see is the group data, right? So if that's the case, we're going to calculate our mean slightly differently. Okay. So here we're going to take the sum of, for every single observation in our data, we're going to take the value that that observation has for our x variable and then multiply it by some weight. Now, quite often these weight represent number of people, right? Or the, in my McDonald's place, number of restaurants, right? So we'll kind of look at a couple different examples and we'll think about, some different things that these weights will be. Generally, it's going to be population or the number of people. And then we'll divide by the sum of the weights. Okay? So here's kind of our steps, right? We first go through each observation, multiply its x value by its weight, right? Um, Usually it's the number of observations you have for that specific value. We then add all those products together, right? We then sum up all of the weights and then divide the sum of the value times the weight by the sum of the weights. And it's kind of step by step. And we'll look at this in Excel and we'll look at this in kind of some different tables here. So let's say I can't see this data. So you can actually go to the census, just Google US Census, and you can get reported average incomes, but not like you can't see the original, the data that they have. You can only get it grouped. So here, like I've got, in this data set, there was 73,000 white males. Their average income was 59,000, or their mean income was 59,000. I've got Asian females, there was 6,150 in the data set, and the mean income across all of them was 39,000. So I've got these different um, groups here. I can only see grouped data. So how would I find the overall mean income for both males and females, right? Well, by what we just said, if I wanted to find the mean for male income, it's going to be a weighted mean. Now, I know that I can't simply add these four numbers up and divide by 4, right? The way I would typically calculate a mean. And that's because, this value of 59,000 represents 73,000 people, while the value of, 60 or 38,000 only represents 11 or 6,000. Represents a much smaller amount of people. So what we're going to go through to is say, okay, look, we want to find the mean income. So this is my X value, multiply it by the weight or the number of people that are in that category for white males. Then add to that the next group's income, multiply by the number of black males that we have in that group. And then add to that the next group and the next group. Once we do that, we'll add them all up. and then divide by the sum of our weights. Well, notice here, if we're using our weights, the number of males we had in our sample was 108,000. That will be our sum of the weights that we divide by. So here, what would I be doing? I'm taking the X value for the first group, multiply by its weight, add to that the X value for the second group, multiply by its weight, et cetera, et cetera. Once I've added those all up, I'll divide by the sum of the weights, which if I didn't have this 108,000 here, you would just be adding those weights up, to get that value. Okay. So we get about what? 53,000 is going to be our weighted mean here. Okay. Now, I've already shown you kind of what it is on the other side for females. But, you would use a very similar, it might be a good kind of thing to do on your own to be able to go through and calculate that female mean income. You use the exact same process. It's just so you'd be using different weights and different X values. Okay. So what if I'm looking at this? So just kind of make another point. Now, instead of by race, like let's say I'm looking at this by region of the country. Now, first of all, these numbers are a lot closer together. So it's not as, it's a little bit different than the other one. So it's not as easy to see. But which of these income values is going to influence my weighted mean the most, right? Well, whichever region has the highest number of people in it or has the highest weight, that's the one, right? When I add it into my numerator, it's going to have the greatest impact on my weighted mean. And that makes sense. That intuitively makes sense. Whatever group is the largest, their income, their mean income should be having the largest effect on your overall weighted mean. Okay. So once again, you could actually, I just put these values in here so you could go through and just some additional practice using this median income as my X value. Here's my weights. I could go through and calculate the weighted mean for males and the weighted mean for females in this region example. But the one that we know will influence it the most will be the South. The one that influences the least will be the mean income for the Northeast, right? All right, so that's not too bad. What if we wanted to do the weighted variance, okay? So the weighted variance for grouped data is going to be pretty similar to what we were doing with the variance, just we have to multiply by the weights. So notice here, sigma squared, our variance, it's going to be the sum of all the deviations squared, but each one of those deviations, we know in our earlier example, the deviation of the white male mean income, there was a lot more white males in the data set than there were Asian males. So we want to weight that deviation squared by whatever weight we have. In the other case, it was the number of individuals in each one of those race, gender categories. I'll then add all those up, divide by the total number of observations. Once again, if I have, thinking about what the total number of observations is, it's really the sum of my weights, right? So if I go back here, what was the total number of observations I had? Well, I had 110,000 like behind the scenes, behind the grouped data, or the sum of those weights, okay? So just to kind of break this down step by step, let's look at the males again, trying to calculate the variance on male income. Well, I'll take this mean income of 59,000. I'll subtract the mean, which was what, 53,000-ish, square it, and then multiply it by, the weight of that group. So notice that's not that far away from the mean, but it represents a lot of people, so we get a really large value here. The second group, while this is much further, their mean income is much further from the overall mean, it represents a much smaller number. So when I take that deviation squared and multiply by the weight, I get pretty similar amounts here. Even though this was evidence that there's more variation in the data, yes, it's evidence there's more variation in the data, but it represents a smaller number of people. Same kind of idea here. Notice this value becomes quite a bit smaller because, first of all, it's pretty close to the mean. It's, I guess it's not actually 53,000, right? It's fairly far away from the mean, but it only represents 6,000 people. Once I have all those standard or deviations from mean squared, multiplied by the weights, I add them all up. The final thing I need to do is divide by the sum of my weights here, right? So, excuse me. All right. Where's that? There we go. Nope, I'm going too fast. So if I add all these up, I'm going to divide. Come on. Sorry. I gotta get away from using my mouse. But add all those up and then divide by the sum of the weights, I should get that value of 94,000. Okay. And I can actually, here, let's copy this just to kind of give you an idea. Let's show you a little bit more behind the scenes here. So just to kind of show you how we end up with this weighted variance, I did break it down in steps a little bit here, but I wanted to be a little more precise and kind of show you in Excel how you can kind of use Excel as like a calculator to do this. So let's go over here. I'm gonna open a new Excel file. Open over here, paste this, increase the view so we can see what I'm doing. There we go. Excuse me. So how was I coming up with these values? First of all, I can kind of get rid of them here. And I don't know why this is bolded. Let's just unbold that. So all I'm doing here, first I'd have to calculate the mean. So if I wanted to find the weighted mean here, one thing that I'm going to need is I'm just going to need every single x value multiplied by the weight. So equals, here's my weight times here's my x value. I could then copy that down so it does it for every single group. I'm then going to add those up, divide by the sum of my weights. Right? And that should give me that 53,000 value that we had in the slides. I then could, to calculate my variance, I'm going to take my weight, I'm going to multiply that by the x value minus the mean squared. Now, when I copy this down, I want the weight and x value to update, but I want to just keep using that same mean value. So I'm going to freeze that cell reference. I just threw $signs in front of there. Remember, you can highlight it, hit Command T on a Mac or your F4 function F4 key on your PC. And then I'm going to copy this down. I could then say, okay, what's the sum of all these deviations squared? But what did I forget to do? Oh, I need to then divide that by the sum of the weights, which kind of represents like the total number of observations behind the scenes, or what's behind this group data. Sure enough, I get that 94 million. Okay. So it's just another way of kind of looking at this in Excel, calculating this pretty easily, pretty quickly, instead of doing this like writing it down specifically by hand. Oh, let me make sure I've got, okay, yeah, I'm on the right one. So I could do the same thing. Once again, I'm just putting some more of these values to give you some stuff to work through on your own. You could do the exact same thing for this female data and reproduce this variance. Notice, there's much lower variation in the mean income across females in this data set than there is for males, right? It's 15 million compared to 94 million. All right. What if instead, and this is slightly different, we had group data, but it was like the data that we were using to create these histograms that we talked about. Well, there I have a range of values. So my frequencies, those will be my weights, because in this category, it represents 15 people. In this category, 47, 45, 47, it represents 19 people. So I can't, I've got my weights, but what are the X values that I use? All right. I'm simply going to use the midpoint of each one of these ranges. So 37, 40, 43, etc. Now, if I'm just looking at this around which is going to have the most influence over the mean, right? It would be, this represents the most people. So this value of 43 would have the most impact on the mean. These would have somewhat of an impact. It looks like there's a kind of like a symmetrical distribution, probably centered around 42, 43, 44, somewhere around there. Now, the variance should be pretty low, because even the largest variation or the largest deviation from the mean, going from like 43 to 37, 6 squared, but multiplied by 4, we should find a much smaller variance, at least than we had when we were looking at income data, right? So, the way that we would write this is thinking about, here I'll use my frequencies as my weights. Here I'll use my M, this just represents the midpoint of whatever that bin is. And then it looks kind of the same. I just add up the sum of that midpoint times the frequency, or X value times the weights, divided by the sum of my weights or the sum of my frequencies. Okay. Now, if I have sample data, I do the exact same thing, right? To calculate my variance. It's just now I'll take those deviations from the mean squared, multiply by the weight or the frequency in this case. But instead of dividing by the sum of the weights, or n, I'll divide by the sum of the weights minus 1. Right? So here, if I had this data, what would I do? Well, I'd go through, right? If this is sample data, there's actually a small, or so then I have the sum of my frequencies is 65, so my n is 65. To calculate the mean, I just go through, take each midpoint, that's like my x value, multiply it by the frequency. So 37 times 4, 148, 40 times 15, 600, so on and so forth. I then add all those up. I get that 2,709 or 2,795. I would then take the sum of those midpoints times the frequencies, divide it by the total number of observations of 65, and I get a sample mean of exactly 43. Okay. So same kind of thing, or same kind of idea as what we were doing before the weighted mean. It's just our weights, our frequencies, whoops, and our x values are midpoints. Now, if I wanted to find the variance, I have to remember there's something else I need to do, right? So I go through and I find the deviation of each bin from its mean, the midpoint of each bin from the mean. So my mean was what, 43? So 37 minus 43 squared times 4, 144. Next group, midpoint of 40 minus 43 squared times the frequency of that group, 135. Well, this one, notice, 43, there is no deviation from the mean. So this category is evidence that there is no variation in the data. Now, obviously, other categories represent that there is some, but this one, specifically doesn't really add anything to that variance because it is evidence that there is no variation for this, these 25 people from that mean. I'll then go through and do that for every single one of these categories, add those all up. I get 522. So, okay, 522 divided by 65, not quite. We're using X bar here. We know that we're looking at sample data. So instead of dividing by 65, I need to divide by 65 minus 1. Excuse me, 65 minus 1, or the sum of my weights minus 1. Okay. All right. So that kind of wraps up grouped data. I have another example that I will show you in Excel, but it's kind of similar to what I broke down, but it's not too specific to Excel. So I think we'll switch over there now, just so I can kind of show you that. Make sure I'm sharing the right thing with you. Yes. So that chapter 3 crime, I put video work here. The original one, it's blank, but we're kind of building it out. So let's say I had this data and I wanted to find the average violent crime rate. Well, I might initially think, oh, okay, I want to find the mean. I'll just add all these violent crime rates up across every state and divide by the number of states I have. The problem is the different states represent a much different, higher or lower amount of people. So what I'm going to have to do is actually find a weighted mean, right? So how will I find this weighted mean, right? Well, I'm going to take the weights times the x values. So here's my weights, the number of people. Here's my x value, right? Violent crime rate. Once again, I could drag this down. It's going to update these cell references to do the same thing for the next observation. But if I get this little black plus sign and I double left click, once again, it copies that all the way down for me. And then how do I find my weighted mean? I find the sum of these weights times the x values. That's my numerator. I then divide by the sum of all of my weights, which is over here is the population. Hit enter, it'll send me right back up, and I get this weighted mean. Okay. Once I have my weighted mean, I can find my weighted variance. Now, here we'll think that we have every single person in the US represented. So we've got total population data. So we won't have to divide by n minus 1. We're just going to divide by n when we're calculating a variance. But what I'll need is the weight of each group times the difference between that group's x value and the mean squared. So here, I'll say, okay, take the weight, which is the population, multiply that by the x value, violent crime rates, minus the mean. squared. Now, when I copy this down, I do want these cell references to update, but I always want to keep using the same value for my weighted mean. So I'm going to put $signs in front of that row and column heading or column reference. I'm then going to double click once I get this black plus sign, does it for every single observation. Now to get my weighted variance, I'll take the sum of all those weights times the deviations from the mean squared. I'm then going to divide that by the sum of my weights. So I can use this sum function. My weights are population. Once again, instead of scrolling up, closing the parentheses, I can hit enter. Yeah, I want to put the parentheses there. And now I've got my weighted variance. Okay. Now, one thing I didn't go through in the slides, but what if I wanted, excuse me, my weighted standard deviation? It is still just the square root of the variance. Right? So same kind of principles of cross over to group data. Okay. All right. So we're going to switch gears a little bit here and move away from group data and thinking about, okay, we now can calculate means, we can calculate variances. One issue that I didn't really dive into is that the variance for income, and I have like values in the thousands. If we look at our examples, we had really high variance values. But when I had like that satisfaction rating variable, where like it was down like in the 40s and 30s, the variance was much lower. So, the value of the variable you're looking at, kind of its average, right, will make it that, if it has a higher average, it's automatically going to have a higher variance. Well, if there is just as much variation, it's going to have a higher variance. So we can't really compare across variables. We can't say, okay, I found a variance in income of 5 million and the variance in human height is 5 inches. Okay, there's way more variation in income. Well, maybe not, right? Because the overall average value of income is much, much higher than the overall average height. So this is my kind of comparison. Just because they have different higher variances doesn't necessarily mean there's more variability in the data. We need to scale that variance. So how can we scale that? We create something called the coefficient of variation, kind of CV to kind of notate it. And all we're doing is we're going to take a ratio of whatever the standard deviation is of that variable to its mean, or the standard deviation divided by the mean. And then we talk about it in terms of like a kind of percentage just to scale it up. We'll always multiply it by 100. All right, so it's going to be this ratio of our standard deviation to the mean. Okay. Excuse me. Now, once we do this, we've accounted for the fact that there's differences in the mean of these variables. And so this coefficient of variation, we should now be able to compare across data sets. So the lower this coefficient of variation, the more consistent the data is, or the less variation there is. So I've got kind of a toy example. Let's say we were looking at crime rate example. So I just chose 5 states just to make it a little bit easy. Let's say I was looking at 5 states. I have reading proficiency, violent crime rates. I can go ahead and calculate the sample standard deviation, the sample mean. Now, if I look at this, notice crime rate has a much higher standard deviation than reading proficiency. But also the violent crime rate values are already much higher than reading proficiency. So I should kind of expect, well, yeah, even if there's a little bit less variation, those values are so large, when I square them, it's going to become really large values. So even though I have a higher standard deviation for this violent crime rate variable, it doesn't necessarily have more variability because it also has a much higher mean. So if I then take the ratio of the two, right, the amount of variation or the standard deviation that there is relative to the size or the average size of the variable, notice my coefficient of variation, much smaller for violent crime rates. That is, we just flipped our decision, right? Just looking at the standard deviation, we would have actually led us to the wrong conclusion when the actual variable that has more variation relative to its kind of size would be this reading proficiency variable. Okay. And there's no built-in for a function, at least I'm not aware of one for this in Excel, but we can calculate standard deviations, we can calculate means, and then just divide the mean or standard deviation by the mean. Okay. All right, the next topic we're going to talk about is percentile. So when thinking about like the different points in the data set, so the mean, median, mode, well, maybe I'm interested in like the 25th percentile or the 75th percentile. So how would I find those values from a data set? Okay. Well, when we talk about percentiles, saying like the Pth percentile is weird, like 75th percentile, that means that whatever value is we're looking at for that 75th percentile, it means that it's greater than 75% of the data, right? Or 75% of the observations in the data set. Okay. If I'm thinking about 100 minus P, that would mean that the 75th percentile, I'd have 25% of the observations above that. Right. So, you've probably seen these percentile charts growing up, going to the doctor. They always have, at least, I don't know. I'm getting a little bit older, so I don't know if they still use these, but, they kind of have like, oh, okay, here's, the 50th, 25th, 10th, 5th percentile for these different combinations of age and kind of height, right? So how do they come up with those values, right? So what we first will do is arrange the data in ascending order. We're then going to locate the position of whatever percentile we're interested in. So the way that we find what position we'll have, say, the 75th percentile, is we plug in 75 for P, whatever our total number of observations in our data set are, and then n plus 1 times P over 100 gives us the position that has the 75th percentile value. If that position is an integer, nice, right? If I find that it's in the 70, if I find that it's in the 321st position, whatever value's in that position, when I arrange the data from in ascending order, that's the 75th percentile value. However, if it's not, if it's like, 23.7, well, then I know that the percentile I'm looking for is somewhere in between the 23rd and 24th position. And in fact, 23.7, it's a little bit closer to that 24th position. So we're going to then do something kind of similar to what we're doing with weights, but we're going to do something called interpolation, right? So we'll go through an example, and I think this will make sense. So let's say I want to find the 25th percentile, and this is a dumb example. I grabbed it from a textbook, but it's a metal funds value, right? It's just a nice small data set to give us to work with. So I've got this really small data set. What's the 25th percentile? Well, first I have to figure out the position. So that's n plus 1. Well, I've got 10 metal funds here, so n is 10. The percentile I'm interested in is 25. If I do that, I get 2.75. So that means the 25th percentile value is somewhere in between the value in the second and the third position. However, I don't simply just kind of find the average of these two to get that. I'm a little bit closer to the value in the third position. So whatever my decimal is, I'll use it to be my weights, right? If I think about being in between the second and third, position, that's a range of 1, but 0.75, I'm a little bit closer to that third position. So I'll take the value in the third position, multiply it by 0.75, take the value in the second position, multiply it by, well, what is the remainder? 0.25. So 0.25 times the value in the second position, the one that I was further from, plus 0.75 times the value in the third position. This is then going to be my 25th percentile. Okay. What if I wanted the 75th percentile? Now, first of all, if I look at this just intuitively, 25th percentile, the value is 4.23. That was the value that was greater than 25% of the observations in my small data set. If I want the value that's greater than 75% of the observations in my data set, I think it's going to be something larger than that value of 4.38, 4.23. So C doesn't make any sense at all. So I'm going to kind of do some work. Okay, well, I've got to find the position of the 75th percentile, right? Oops. I thought my animations were on, but they're not. So we'll just go through this step by step. So I plug in that n of 10, 75th percentile, P is what I'm interested in. I get a position of 8.25. Well, now it's kind of tricky, right? If I end up with a value that's has a decimal less than 0.5, well, notice the 75th percentile is actually a little bit closer to the 8th position than it is to the 9th. So I'll still use the decimal to get my weights. My weights should be 0.25 and 0.75. But because I'm closer to the 8th position, that value should actually be getting the higher weight. So the decimal will tell me the two weights I use, and then I have to use my intellect to say, okay, well, 8.25 is closer to the eighth position. That's the value that should be getting the higher weight. So 0.75 times the value in that eighth position plus 0.25 times the value in the ninth position, we get that 75th percentile. Okay. All right. I'll draw something out for you here. I don't think I have anything. Let me see. I don't think I have any. Yeah. So just some terms that we'll go through. And then I'll show you something that won't dive into too much in this class, but you might see it pop up in other classes. So I can find the 25th, 50th, 75th percentile. First of all, that 50th percentile, well, that means that it's greater than 50% of the data. That's literally our definition of the median, right? There's 50% above, 50% below that value. So we could use this method to find the position of the 25th percentile, 50, 75th, and then calculate what those values are. We then have this thing called the interquartile range. So this interquartile range is just the difference between our first and our third quartile. We then take whatever that difference is to get our lower limit, right? And this is how we can reject certain things as outliers. So is it so, I've got this, distribution, but is this one observation just so unlikely that we really should rule it out? There must be something weird going on with how it was collected. It might be a correct value. So we'll take that first quartile, subtract 1.5 times the interquartile range, take the third quartile, add 1.5 times the interquartile range. Okay. So in our example, we had values of what? 47.7 and 4.23. Okay. So what I'm going to do, if I think about this, so we've got .47. So our third quartile was 47.7. Our first quartile was 4.23. So our interquartile range is going to be 47.7 minus 4.23, which I'm going to cheat and use Excel to be my calculator here so I can be lazy and not do this math in my head, but also to make sure I'm getting the right thing. So this is what? 43.47. To then get my lower limit, I'm going to take my first quartile and subtract 1.5 times that interquartile range. So I've got what? 4.23 minus 1.5 times 43.47. So I do that. So that's what? 4.23 times 1.5 times. So hold on. So negative 60.98 approximately. I'm then going to take my upper limit is the third quartile plus 1.5 times that interquartile range. So 47.7 plus 1.5, times 43.47. So this is what? 47.7 plus 1.5 times this value. 112.91 approximately. So I've now got my upper and lower limit. Essentially what I'm saying is if I see any value in my data that's outside of this range, I can rule it out as an outlier. So if I saw a metal fund's value and it returns, I don't know, 200%, I could reject that observation, say it's likely an outlier. Now, if I think I look at this exact example, all the values are actually in between this range. So there's nothing that I can rule out as an outlier. But let's say, that one of them was 200. We could rule that one out. We shouldn't be using that in our calculation. This is what we would call the Q test, right? It's the test for whether or not we can get rid of these outliers. Another thing you might also see is that we call a box and whisker plot. So it's going to be very similar. It's actually, I could probably do it the same thing. We'll plot the lower and upper limit. We'll then also plot the first quartile. So this is at what? 4.23. We'll also plot the third quartile. Draw a box around these 43.47. And then usually you'll see the median or the second quartile, which I don't have here, but if we did, you would plot it somewhere here. Right? So it kind of shows you, okay, here's the median, here's your interquartile range, here's your upper and lower limit for what you can reject. If anything's outside this range, we can reject that as an outlier. Okay, so that's called often a box and whisker plot. Right? Excuse me. All right. So with that in mind, let's keep moving here. So we have these metal funds values. I talked about this. Oh, and then this is I'll try to throw in some great memes along the way throughout this course, but please don't reject me as an outlier because you are the Q test. So the Q test is just what we use to reject outliers. Terrible joke, I know. So the next thing that I want to introduce is the idea of z-scores. So how many standard deviations away from the mean a value is the literal definition of a z-score. So we'll see their importance and use them a lot more later on in the semester. But for now, just know that we can calculate this thing called a z-score that tells us how far away, how many standard deviations away from the mean a certain x value is. It's really all we're doing there. If you're thinking about, let's say I had a mean of 50 and the standard deviation was 10. Well, if I see an x value of 70, okay, how far away from that is the mean? It's 20 away. Well, how many standard deviations is that? Well, if I'm 20 away, the standard deviation is 10, that's 2 standard deviations. Well, what's the actual formula that I'm using in my head to calculate that? Well, it's whatever the difference between that x value and the mean is divided by the standard deviation. That is a z-score, or that tells me how many standard deviations away from the mean that x value is. And we can do it for population or sample data. So what would the z-score for the mean be? Well, how many standard deviations away from the mean is the mean? 0. So we should end up with a z-score of 0. Right? What about values above the mean? Well, they're going to be a certain number of standard deviations above the mean, so they should have positive values. What about values below the mean? Well, if the x value is below the mean, then this numerator would be negative. Standard deviations, we said variances and standard deviations, always positive. So a negative value divided by something we know is always going to be positive, values below the mean should have a negative z-score. Okay. There's an empirical rule that we'll kind of use a little bit. You'll see it pop up in the homework. And this idea is that if I have these z-scores, right, what I end up knowing is, okay, so if I think about the area under this curve is going to be 100%. So I've got some frequency distribution. I know that this represents every single observation. If I go one standard deviation above and below that mean, whatever those values are, it'll always be such that there's approximately 68% of the observations within that range. So if I'm interested in this, like, okay, what's the range of values that's one standard deviation above and below? Or what's the two values that, would give me 68% of the observations being between them? It'd be whatever values are one standard deviation above and below. Once I have the mean and the standard deviation calculated, that's pretty easy to find. 2 standard deviations, well, I'm going even further away, right? So it should be that there's even higher likelihood that I'm seeing values fall within this range because I'm going 2 standard deviations below, 2 standard deviations above. Approximately 95% of our data will fall between 2 standard deviations of the mean. And then what about if I go 3? Well, now we're up to like almost 100, right? So it's almost like a guarantee that something, if I calculate this range of values, 3 standard deviations above and below the mean, there's a 99.7% chance 7% likelihood I see a value 3 standard deviations in the range of 3 standard deviations above or below the mean. What if I go out to 6? Well, you might have heard this in the Kelly's, if you're in Kelly or you're even interested in the business world, you probably have heard of the 6 sigma, right? You can get 6 sigma certified. Well, standard deviation, that is sigma, right? Sigma squared was the variance, sigma. So 6 sigma going 6 standard deviations out to the left and the right, man, we're really close to 100%, right? So that's the general idea. We can then, how do I find what these values are? Well, you can use the inverse transformation, okay? So we can convert these different values for X into a Z-score, but we can work the other direction as well. So notice if I just rearrange this equation a little bit, I multiply both sides by the standard deviation, I then add the mean to both sides, I can back out the X value. That would be a certain number of standard deviations above the mean. Right? So let's think of an example here. Let's say I had some exam scores and they had a mean of 72. I have a variance of 64, right? What is the range of test scores that will include 95% of the students around the mean? Well, if we go back, we said, what would give us approximately 95% of the observations, what range, going 2 standard deviations above and below the mean? So we're going to use that Z-score of 2, right, and -2. So we're going to go 2 standard deviations below, 2 standard deviations above. We plug in our mean of 72. We need our standard deviation. So if we're given the variance, we can't plug 64 in here. The standard deviation is the square root of that. So I take the square root of that variance of 64, I get 8. So my lower value should be, what, 72 plus that -2, I'm going 2 standard deviations below, times whatever the value of the standard deviation is. I get 56. To get the upper range or upper value, 72 plus 2 times 8, or 88. So what I could say is I just determined when I go 2 standard deviations above and below the mean, there's a 95% chance that if I chose a test score at random, it would be in between the two values of 56 and 88. Okay. All right. Almost finished with this chapter. We have one more topic that we'll go through, and then I'll kind of have a little bit of Excel work that we haven't done yet, looking at correlations. So we've only talked up to this point really about one variable. So a lot of the times what we might be interested in, okay, what's the relationship between two variables? So if I want to know, if one variable increases, does the other variable tend to decrease, or does it not do much of anything, right? We've got two kind of simple measures, which are the correlation coefficient and the covariance, okay? So we've got our first we'll talk about is the covariance. So we've got a population sample covariance, right? We're looking at population or sample data. So the setup is going to be that I've got these two variables, right? X and Y. We'll end up putting some, actual variables here, but for now, just X and Y. What we're going to do is go through, and maybe this is someone's income and years of education. So we find the average income, the average years of education. For every person, we'll go through and figure out what is their deviation from the average income, multiply that by their deviation from the average years of education. Do that for every single observation, add them all up, and then divide by n. Same kind of idea for the sample. It's the exact same thing. Sample covariance, I just divide by n-1. So same kind of principles we were using for the variance. Now, what does this covariance mean? And I'll kind of go through step by step to explain a little bit more as to why. But for now, we'll just say, okay, if I find a covariance that's positive, and the way we write these covariants, I forgot to say this, right? Sigma and S, it looks like standard deviations, but I'm writing two subscripts here, right? It's the covariance between two variables. So if it's positive, that tells me that as X goes up or as X is higher, Y tends to be higher as well. If I have a negative covariance, that means that as X is higher, Y tends to actually be lower. And then if I have something that's approximately 0, it means that as X is higher or lower, the value of Y doesn't really change by very much. Okay. So why is that the case? Like why did the positive and negative relationship or covariance tell me about that relationship? So let's think about a data set. I had some CDC data, and it was just on height and weight, right? Now, in our heads, we probably know, well, if you tend to be taller, you probably tend to weigh more on average, right? So there's probably a positive covariance here, but we'll see why. So think about, if I had height, the mean is what, 64 inches, the average weight, about 188. This first person is quite a bit above the average height. However, they're up below the average weight. So this one person is evidence that when your height tends to be taller than average, your weight is actually lower than the average. So this would mean that being taller has associated with a lower weight, or that there's a negative relationship. So what does it add to the numerator? Its deviation from the mean of height is positive, times the deviation from the mean weight, well, that's negative. So we end up with a negative value. Anytime these two variables for a person are on either side of the mean, on opposite sides of the mean, we'll end up with that as evidence that when one of those variables is higher, the other tends to be lower. Now, that's just one observation. We're then going to go through the rest of these. We'll notice this person, slightly below average height, below the average weight. Well, here, their deviation from the mean height is negative. Deviation from the mean weight is negative. That means, oh, these two variables, they tend to be on the same side of the mean. This observation is evidence that when X is lower, so is Y. And then we keep going through this person, first of all, yikes. But I guess, they're relatively short. So this person was quite a bit below the average height, very much below the average weight. So notice the value that gets added in for them. This is an observation that has strong support for that there's a positive relationship between these two variables, that they both tend to be on the same side of the mean. Notice even this variable where they were on opposite sides, yeah, it was adding a negative value, but it was a pretty small negative value relative to this one. So observations that provide stronger evidence that these two things tend to be on the same side of the mean, they will kind of influence that covariance a little bit more. And then we kind of the last one, it's another person with below average height, below average weight. We get another kind of evidence from this observation that these two things tend to be on the same side of the mean. If we go ahead and do that for every single observation here, I think I end up with a covariance of 76, which is really saying that on average, these two variables tend to be on the same side of the mean. Okay. So is this a strong relationship? If I calculated this covariance, and I'll show you, we can do this in Excel, but if I calculate, is this strong, 76? Like, well, it's kind of weird because what are the units of our covariance? If I think about my height weight example, I've got height times pounds. So my covariance is like inches times pounds. So my covariance is like inch pounds. If I had the years of education income, it'd be dollars times years. I've got year dollars. This unit doesn't really make a lot of sense. I can't compare the relationship between, say, income and years of education to the relationship between height and weight, unless I scale it, right? So what I'm going to do is I'm going to scale my covariance. And when I scale it, we'll end up with a new statistic called our correlation coefficient. So all we're going to do to get this correlation coefficient is take our covariance and then divide it by the standard deviation of each variable. And kind of think about this, isn't like the most technically correct way to say it, but it's like we're accounting for the variation that exists in both of these variables. And notice if I'm dividing by inch pounds, I get rid of my units as well. So by dividing by the standard deviation of both variables, I'm accounting for the fact that there is some variation that exists in these two variables. The variation in income is much, much higher than the variation that we see in height. So I know the covariance is likely going to be a lot higher when I'm looking at the income, covariance with something else compared to height's covariance or something. So once I scale these by dividing by the standard deviations, I end up with a correlation coefficient that's always between 1 and -1. Right? And you can kind of imagine why, notice here, what's in the numerator for my covariance? It's the deviation of X times the deviation of Y. What's the numerator of my standard deviation? It's the square root of the sum of the deviation of X squared. So you can imagine how things are going to cancel to where we end up with a correlation coefficient that's always between 1 and -1. We won't go to the proof in this class. If you're really interested in it, I'm sure you can kind of Google why correlation coefficient is always between 1 and -1 mathematical proof, and it would have step by step, right? But for us, we know that we're just scaling it down so that we now have this nice measure between 1 and -1, 1 representing the strongest positive relationship between two variables, -1 representing the strongest negative relationship, and then 0 being our no relationship. So now we can kind of compare, right? So let's say, I go through and I couldn't, calculate the standard deviation for height, standard deviation for weight from that CDC data. To get the correlation coefficient, I would just take that covariance of 76 that I found, divide it by the standard deviation of both of those variables, and I end up with a correlation coefficient of about 0.45, which is, if one is the strongest, zero is no relationship, it's a middle of the road, right? It's a pretty strong relationship. And that makes sense. What we know about, just, the laws of physics, right? Being taller and having, just being more likely that you have a higher weight as well. We could also compare this. So let's say I had that covariance between height and weight. I just said it was what, 0.45, I think. Let's say I had the covariance between years of education and income, and it was 0.8, right? Well, now I can directly compare these relationships. Yes, they're both positive, but the relationship between education and income is stronger than the correlation between height and weight. I don't know if this is actually the case, but the hypothetical values. Okay. All right. So, oops, back to sharing my screen. Excuse me. Really kind of what we're doing with this correlation coefficient is we're trying to pick up, we talked about before when we have these scatter plots, we're trying to say, is there evidence that there's like a positive? Well, here it looks like between height and weight, if I plotted every single person in that CDC data, yeah, it looks like there's kind of like this positive relationship. That's what that correlation coefficient is capturing, right? Well, so this is just a simple, easy one. Just some sample questions you got to work through as you're getting ready for the homework or for getting ready for the exams. But if I had a covariance here of 330, I've got the variance on both of these variables, and I'm thinking about height and weight once again, 8.13 and 48. What would my correlation coefficient be? It would just be 330. Oops, I can go back here. 330 divided by 8.13 times 48.51, I end up with about 0.84. And then it's okay, what about the relationship between hourly wages and some beauty measure? That's kind of weird, but I'll explain why. I'm using an example in a second. So I've got pretty big sample. I've got this covariance of 0.18, but notice, yeah, just because the covariance is smaller, well, these standard deviations are pretty small too. So what will I do? Well, I'll take that covariance divided by both the standard deviations, so 0.18 divided by 0.68 times 4.66. Now notice my covariance is positive. If I'm dividing it by standard deviations, the sign of my covariance should always be the same as the sign of my correlation coefficient. So I know that D doesn't make any sense here, right? Because I've got a positive covariance. I also know 1.2 doesn't make any sense. Why? Because we said the whole point of this correlation coefficient was to scale it so it's between 1 and -1, and we can compare relationships across variables. So if I go ahead and plug those values in, I end up with 0.06. So what could I say? Well, I could say that for children, the relationship between height and weight here, actually, yeah, this was child height. Yeah, so the relationship, actually, we can do tons of things. So here, this was CDC data on all like adults. So the relationship between height and weight for adults is much weaker than the relationship between height and weight for children. And what's even weaker than both of those is the relationship between somebody's looks or their beauty and their hourly wages. So the reason why I use this example, and I'm obviously not going to like play the clip in this video, but if you're interested, I put the link up there. It's very funny. It's meant to be comedic, but this is like an old Daily Show clip about this economist who was looking at really what this relationship is. Like, are people who are deemed by the average person as more attractive, do they tend to see higher wage premiums? Are they paid a higher? But notice the strength of the positive correlation coefficient for men much smaller than for women. So I think what they actually, one of the studies that they actually did was they took all these photos and they like sent them to 100 random people and had them rank them from like 1 to 10 on what their attraction rating was. So then across all these 100 people, they then had who was the most attractive, who was the least. They then sent these photos out with LinkedIn resumes, but all of the resumes were identical. The only thing different was the picture that was in the LinkedIn profile. And the picture for the LinkedIn profile if it was rated by these other people as more attractive people, so people in the higher percentiles of attractiveness, they saw that they got a higher number of interview requests, especially for women. The men received slightly higher, right? But there was really this strong relationship between attractiveness and the number of interview requests for the exact same resume for women here. Now, this is obviously like, we've just discovered evidence of something that shouldn't be going on, right? That, we shouldn't be rewarding people just for their looks. Whatever job they're getting should be based off of their merit. But I don't know, just kind of a fun, interesting example. I don't think I will do a separate Excel video, or if I will, I'll splice them up. But we'll kind of round this out by looking at, here, I'll get rid of this. Oops. Make sure I'm showing you the right thing. Sorry, it's a little bit clunky for me. Zoom, it's harder for me. So I'm going to zoom in so we can actually see what I'm doing here. And I'm on this correlation tab, right? So I've got population and violent crime rates here. And I'm just going to say, okay, what's the correlation between population and violent crime rates? Right? So, or here first, what's the covariance? Okay. So there's this built-in covariance function. Now, if I type this out, notice it starts to suggest things for me. I can click on them, or if I hit tab, it automatically selects the first one. I'm going to treat this as population data, just because. So is there, we could do sample and we'll see how that changes things in a second. But basically, I'll first select, well, what's my first variable that I want to find the covariance between? So the first one is population. So I'll select that. And then as I have higher populations, comma, what is kind of the relationship between the violent crime rates, right? So if I get more people shoved in the same area, am I seeing increased crime rates? So I'll then put comma and select my second variable. Now when I enter, this should give me my covariance. Now notice, this covariance is huge, really like, oh, huge, strong, positive relationship. Well, the population variable is very large values. So what we would want to do is find our correlation coefficient. So what do we need to do that? Find the standard deviation of both of these variables. We talked about this already. That's STDEV dot P for population. So I'm going to find standard deviation for my population variable. I'm then going to find STDEV.P, the standard deviation, population standard deviation for my crime rate variable. To find my correlation coefficient, I'm just going to take my covariance and divide that by the standard deviation of my X variable times the standard deviation of my Y variable. Now notice, oh, this isn't that strong, right? If I'm thinking about between 0 and 1, 0.19, I'm on the lower end of things. Okay. But yeah, this is how you kind of do covariances in Excel. And just to kind of make the point, if instead, this is every state, but I don't know, let's just say we didn't have every state here, or maybe I'm only using states, but I'm interested in like the world covariance between population and violent crime rates. What should be true if I do a sample covariance here relative to when I was calculating the population? Well, the calculation is going to be exactly the same. The only thing that changes is our denominator, right? Instead of dividing by n, we divide by n minus 1. So if I go ahead, select my two variables again, so variable population, comma, variable of violent crime rates. When I hit enter here, I should find a covariance, a sample, I put correlation coefficient. I should find a sample covariance that's a little bit smaller, right? So, or sorry, I said smaller. We're dividing by a larger value, or a smaller value, right? So n minus 1, so instead of 50, 49. So my fraction is going to be larger. Sure enough, it goes from, what, 172 million to 176 almost million. So just kind of reiterating these differences between the population and sample calculations. But, in practice, it's either sample data or it's population data, right? I should only be calculating one of these, whether or not I've got population in every single state or I don't have every single state. That would be a sample. Okay. So that should round out all of the Excel work and all of the theoretical work for chapter 3. We'll move on in chapter 4 to probability.